First, it's a pleasure to be here, and thank you for coming at this late hour. Thank you, Miranda, for the introduction, Jim, and also Richard Love, who's had a lot to do with this lecture. And then finally, I need to thank the Kavli Foundation, and especially Mi-Young Chun, who's the Vice President for Science Programs, and Christopher Martin. They have a real vision for the Kavli Foundation, and you're going to see a lot of great things coming from them, because I had the pleasure of spending time with them today, where they mapped out their future vision for the foundation. And so today what I like to do is talk about this artificial leaf. I'm glad Miranda mentioned that my research advisor, Harry Gray, because it always starts with your teachers. And Harry, when I was a graduate student, instilled the whole energy bug in my blood, but really challenged us, and there was a whole cohort of students, all who have gone on, and stayed committed to the problem, because you got to remember in the 1970s, science energy went away. It was gone again. And I had no conferences to go to. Isn't that sad? So I couldn't go to any Gordon conferences. All my friends became organometallic catalyst chemists, and I just kind of hung in there on energy. And that's something Harry taught me, and so I like to thank him. So today what I'll do is talk about this issue, the artificial leaf. And before I do, since it's kind of a general lecture, you can see I give lots of public lectures because I have to spend a lot of time finding pictures on Google that are evocative of the image I'm trying to show. The Holocene is something that you're living in now. It started 10,000 years ago. But it was a time, and it's a period, an epoch, geological epoch, and it's where humans weren't really affecting the world because there weren't many of you. And we still live in the Holocene, but now there's this new word that's cropped up since the 70s, and it's called the Anthropocene. And the basic issue is there's so many of you, you've actually started affecting life systems, right? So you're in an adverse way affecting the world because there's just a lot of you. And the reason I bring these two epochs up is because I think this community, chemistry, can start a new geological epoch. And it's actually something that's been discussed by an Australian physician, Brian Furness. And he calls it the Sustainocene. And the Sustainocene is what you would think sustainability, and you always think ecological sustainability or environmental integrity, climate change. But Furness said that's not enough. There is one other piece of this, and it's you. It's the people. And you can't have a sustainable world if you have a bunch of poor people in the world. And you can't have have-nots. And as the world develops, there's a bigger chasm between the haves and have-nots. And he's saying that's just not sustainable. And so one thing I'll pose to you today is this community can actually start a new epoch in humankind. Let the physicists do their thing. Who cares? The chemists can actually start a new geological epoch. And it's by giving food, water, and energy to the poor of the world. And by doing that, you empower them, and then they can start rising, and they can make money, they can become educated, and you start narrowing this divide. Now, why did this kind of hit home for me, Brian Furness's view of the world as Sustainocene? Because for energy, if you don't take care of these poor people, you're going to be in big trouble. So the energy equation has three terms in it: population, gross domestic product per capita, how rich a country is, and then energy intensity. Can you grow your GDP and use less energy? That's conservation. And it turns out you're all energy users, if you can calculate it, the number of calories you take in 24 hours and then calculate power, joules per second. And you're going to find out that you're all 100-watt light bulbs. And that's why you look so bright and shiny to me right now from up here. As more of you show up, of course, you're going to need more energy. And it turns out the numbers, and so remember, this is power, so I like talking about power energy per unit time. And you're burning a big light bulb in the world. You're burning around a 14 trillion watt light bulb right now, and you need to give energy to that light bulb to keep the light bulb on globally. And in the next 40 years, you're going to need around 16, 15 more terawatts worth energy equivalents. And so you're going to double your energy. In that calculation that I did, I assume, by the way, you're going to save all the energy you're using today. So you're going to need 16 terawatts, 15 terawatts equivalents of energy, and you're going to be saving 14 terawatts in the next 40 years. So I chose a very aggressive energy intensity number, this last number, EGDP. And so then the question becomes, and now you're going to see how this folds into Furness's idea of the Sustainocene. If you need 15 more terawatts and you're saving all your energy, what's going on? Why? You're good citizens, science is going well, you're figuring out how to save energy, and it's because it has nothing to do with you, right? It has to do with the people we don't see in our lives, the poor. And so there's 3 billion people that are low energy users. Actually, people have been trying to give energy to the poor for 40 years, and there's more people than ever, 1.6 billion people without even electricity. So something must be wrong in terms of our approach. And then there's around 1.4 super low energy users, and there's 3 billion new people to come, and they're coming into that part of the world, so there's 6 billion new people who are going to need energy. And if they start reproducing what you've done and use coal, oil, and gas, the world's going to be in deep, deep problems. And if you think you've seen climate change so far, wait till you see what you'll be in for. So it's to your advantage to start taking care of these 6 billion people, and that's this issue of the Sustainocene. You have to take care of those people if you want ecological sustainability. And then the question becomes, what have we really been doing wrong to get these people energy? Because, like I told you, the number's growing of people without energy in the world. And the problem is the way we do science. So we get funded from federal agencies, industry, and you take care of problems for this world. You guys are wealthy, and because you're wealthy, you can demand high-performing things. And it turns out, when we want to go to the poor, what we do is, I was at MIT, engineers abound. You take whatever you have and you re-engineer it, and you take the proverbial square peg and you pound like heck and you make it go into that round hole. And it turns out, if you start with these energy systems and start re-engineering them, first they're expensive to begin with, and then they just get more expensive. So that's why this hasn't been working. When we do science, I call it EST science, S science, the biggest, the fastest, the tiniest, the smallest. Once you start doing that, you're going to be talking about cost. So what you really need to do, and this is kind of a nice thing, you need to start inventing new science, work from the ground up. Like, take a plain piece of paper and say, what science do I need to invent to start getting costs out? And a simple measure or a metric for cost is how much does it weigh. It's that simple. So I sometimes say, this is what Harry actually still does experiments. I've become totally useless. I sit in my office, I go on Google and I make Google plots, and then I run into the lab and I tell my students, look what I just discovered, and then I say, go back into the office, no sir, and leave us alone and let us keep doing science. So I'm going to show you one of my latest discoveries from Google. And what I did is I took just something like a Boeing 777 and I said, how much does it weigh? And then how much does it cost to manufacture? And how many did they make? And in 2006, there were 74 Boeing 777s made. Then I did it for etching tools, machine tools, and automobiles. And you get this curve. And without knowing anything about the sophistication of the technology, I can start predicting price. And what you find is things that weigh a lot cost a lot. And there's kind of a Darwinism of materials research, in case you've never thought about it. Almost everything comes out to $10 per pound. Now, it doesn't work for pills, pharma. It doesn't work for Intel chips. It doesn't work for commodity chemicals, but it works for machines, and this is how you build energy systems. And there's a magic number, $10 per pound, and that's basically stuff, right? It's stuff you dig out of the ground. It's wire, it's cement, and it comes out to $10 a pound. And it works for lots of things, like I said. And one of them, for instance, you can say Boeing 777s don't look much different than automobiles. This is true. I did call McDonald's, and I found out the weight of the patty, the cheese, the bun, and the lettuce. It's $10 per pound. All right, so McDonald's hamburgers, to me, don't look any different than Boeing 777s. Now, when you look at this graph, we're kind of simple thinkers. We say, how do you guys build energy systems? What you do is you build one thing, a power plant, for instance. It's centralized, it's heavy. You multiply $10 per pound, how heavy it is, and it comes out to around $1 billion. So if you want to build energy plants, you got to put out around $1 billion. And that means you need a high CapEx cost, capital expenditure costs, and then I set up some business model and I get a return on my investment. And thank God, that's how we build energy systems in the legacy world, meaning you're a legacy because you inherited an energy system, and now it sits like an albatross around your throat. The poor don't have anything because they don't have a lot of money to pay the big capital expenditure. So that's actually what is saving us right now. And so the real goal becomes not to build energy systems for them the way we built them for us. And if this part of the curve isn't working for them, this is science. If that end of the curve isn't working, turn your eyes to the other end of the curve. And the question is, can you start building energy systems like a hamburger? All right, so that's what I'll talk about. When I look at the artificial leaf, to me it's, could I build the hamburger of energy systems? Now, why do I care about weight? Because of cost. And that means I need to start thinking, if I'm going to do science discovery, and I want to innovate things, I should start thinking about what's the lightest lightweight materials and things I can make. And look at all these things here. These are all ways you can store energy, right? So I could have a solar panel on your roof, and I could pump air into the ground and compress it. And then it basically run the compressor backwards, that's a turbine, and you can generate electricity at night. So I could take compressed air energy storage and then run it at night. You'll get electricity. What you see here is that compressed air is 0.5 megajoules per kilogram. That's how much energy you can store. And by the way, I published this in Chem Reviews, and most of the articles on mechanical engineering, how flywheels work. And every reviewer pointed out to me that it was Chemical Reviews. And no, sir, it's not doing chemistry, so they rejected the paper. But you have to know who your competition is. So these are mechanical engineers. So they're tough. This is a tough crowd. And they're doing as well as people who do batteries. Look at batteries are 0.5 megajoules per kilogram. These are low energy storage devices. it's always been chemical bonds that you store most of your energy, because you get most of your energy density, bang for your buck, in a bond. It's kind of interesting. My entire talk today is freshman chemistry. So look how these look complicated. If I did energy storage for a battery and put an electron on a metal atom, because charge goes into the metal atom, so you take charge out, and I took the density of a solid, and then I put some number of electrons in there, then take the volume of a 2-electron bond versus the volume of putting electrons on an oxide lattice, you get that difference in energy density, 100 to 1,000 times more energy dense. And you know that because 100 years ago you decided to use fuels. You didn't use batteries. Now, you should use batteries if you're a car company, and if you can make your car go 4 times longer on a battery, you're going to become incredibly wealthy. Right? So you should do that. But you're not going to take care of storing 16 terawatts worth of energy for poor people in batteries because of that low energy density. So this is kind of a nice thing, because we're chemists and we deal with bonds, and that's where you're storing most of your energy. And if you don't like using technology as your benchmark, of course you can use biology, and that's photosynthesis. So photosynthesis stores energy, and from grade school you remember light, sunlight, plus water, plus CO2 gives you oxygen and sugar. What most people forget is all the energy storage in photosynthesis is in water splitting water to hydrogen and oxygen. If you calculate delta G, you'll find out for the full cycle of making the carbohydrate that the carbohydrate only stores 1% more energy than water splitting. So when you fix hydrogen with CO2 in the plant, and the plant keeps the electrons and protons separated so you don't get gaseous hydrogen, but hydrogen equivalents, when you rearrange the bonds of water to make hydrogen and oxygen, that's where all the solar energy is being stored. The hydrogen's untranslated with CO2 as a hydrogen storage mechanism to make sugar. What do you guys do today? You're going to eat food, you're going to chew it, and then what's going to happen? You're going to make CO2 come back out. The carbohydrate's going to go to CO2 plus hydrogen. Hydrogen and oxygen are fed to your mitochondria, where you have cytochrome C oxidase, and you run the fuel cell reaction. So when you look at the full energy cycle, all the atoms are balancing. CO2 plus water. Water goes to hydrogen O2 with solar input. You eat the sugar, get CO2 out, breathe in the oxygen from the plant, take the hydrogen, recombine it inside you. So when you eat a green leafy vegetable, if you do the mass balance, there's only one new mass in the entire energy equation. It's the sun. So I don't know what you think you're chewing when you eat food, but you're chewing the sun, and then you're releasing it inside you. Do the mass balance. You'll see the only new mass is sunlight. So this has worked for 2.5 billion years. You guys decided to do a 150-year experiment using coal, oil, and gas. I am the ultra-conservative. I'm not a liberal. I'm conservative because I want to work and use what's worked for 2.5 billion years. And these very liberal people called oil companies, because they're doing a 150-year-old experiment. Right? So I'm the conservative in the energy argument when I say use the sun. So that's why you use things and you want to make a fuel, and that's why photosynthesis made a fuel. So let's get into now how would I duplicate photosynthesis. And what I'll do is not worry about every one of these cofactors. Each one of those occupy research groups from all over the world. I'll break photosynthesis down into a systems engineering problem. Sunlight in, I do charge separation, I move an electron one direction and a positive charge the other. So moving charges is current, no wires. Then the plant stores one electron, one hole, driven by the sun. So the sun's made a high potential current. And then it's a battery. it stores 4 charges in the oxygen evolving complex. It stores 4 electrons in the other cofactor. But then the plant says, I need more energy density. I just can't keep putting charge on cofactor sites. So then it translates the battery into the chemical reaction of water splitting. So if I wanted to duplicate this process at a systems engineering level, I need to bring light into a material that makes a wireless current, store 4 units of charge, 4 electrons and holes, and then translate that into water splitting. And I'll store 99% of the solar energy just the way sunlight works. Now, to do that, you have 2 options. For 45 years, this is the option that most of science has pursued. And what this is called is a Gerischer cell, photoelectrochemical cell. And the way this works, and this is still a large research area, sunlight comes in to the semiconductor, absorbs the light, and it does water splitting. So in the Gerischer cell, the material that's doing light absorption is also doing catalysis. That isn't how photosynthesis works. If you look at this plant, it's separated function. It does light harvesting up here. I'm not showing the light harvesting complexes. Then the sunlight comes into the membrane, which is the semiconductor in a sense, to generate the charge. And then it slaps 2 catalysts at the bookends, at the anode and cathode effectively. So the plant separates charge. These photochemical devices aren't like plants, because you're trying to make one magic material that does everything. It's hard enough to design a material that absorbs the solar spectrum, never mind trying to do the complicated 4-electron, 4-proton catalysis. And when you do that, you see things like this in the applied physics literature. If I'm going to do water splitting, it's a 1.25 volt reaction. I have to make sure the band gap of the semiconductor straddles the oxidation potential. So, for instance, this material here, silicon, it can make hydrogen, but it can't do water splitting because it doesn't have enough energy in its band gap. And so what you find is there's even a sadder story with this approach. Not only do you have to make the thing absorb light and be a catalyst, it has to have a band that straddles the water oxidation potential. What I'm about to tell you today with the artificial leaf, it's a different concept. In that, you separate function. Put the photovoltaic between 2 conductors, so I'm burying the junction, it's called buried junction, and then on the conducting layers, I'll put my catalyst. The beauty of this is very modular. I can design semiconductors separately from catalyst design, and then I got to put it all together. And there are new problems here because you're going to have to get charge across the interface into the catalyst, so there's a lot of interfacial charge transfer issues. But the beauty here is I can do catalyst design separate from semiconductors. The other thing is, because it's between a conducting layer, you don't have to straddle the potential. As long as you have 1.25 volts or whatever chemical reaction you're running in solution, it will automatically adjust. Effectively, the band gap will automatically adjust to the chemistry you're doing in solution. This actually was a concept pioneered at NREL, Art Nozick and John Turner, right? So this has been out there, but people kind of forget about it, and they were enamored with this Gerischer cell. So we return to this issue of a buried junction. Now, the hard part, if you're going to do photosynthesis, is water splitting. I'm showing some students here, and Miranda mentioned proton-coupled electron transfer. You need to be an expert in proton-coupled ET. It's a simple reason. Electrons are quantum mechanical. They spread out. Protons are classical. They don't spread out the wave function. And so electrons can go a long distance. Harry Gray, long-distance electron transfer. Protons can't. And as soon as the electron gets decoupled from the proton, you start building in a big energetic barrier. So you need to couple on the same length scale the electron to the proton. to get minimal energy barriers. Water splitting is a 4-electron, 4-proton process. So that makes it hard, and you're breaking a lot of bonds. You can go on Google and get an electrolyzer, buy an electrolyzer from Google. They've been known for almost 150 years. And you'll find there's 2 flavors of electrolyzers. Electrolyzers that do this catalysis out of a glass of water. Then you need expensive materials because catalysts decompose, so you're stuck using iridium, platinum, ruthenium. And then you have expensive membranes. Alternatively, you can work in concentrated base. There in concentrated base, the catalyst exists, doesn't corrode. But then you're under harsh engineering conditions, and so you have a heavily engineered electrolyzer. The other thing is electrolyzers are EST science. They are really great at making a lot of hydrogen and oxygen per unit time. They can run over 1.5 amps per centimeter squared. The sun only comes in at 30 milliamps, so it's overkill. So we decided a few years ago, could we take the best of both worlds? Could I make a catalyst that's cheap, a cheap oxide, say, that also works in water? So we won't use expensive or critical materials, and we'll be able to work under simple engineering conditions. And if you do that analysis in your head, I'm going to have to make a catalyst that doesn't corrode, which sends you to a point to say you need to make a self-healing catalyst. So as the catalyst is working, it might break down, but we'll let it reform again. If you can do that, you could work out of a glass of water. And if I can work out of a glass of water, I don't need a heavily engineered system. I don't need a bunch of what's called balance of system. I don't need a bunch of weight. I'm headed in the right direction to be cheap and highly manufacturable. So we set out to do that. To do water splitting, that's 1.25 volts uphill. We decided that was too complicated to bite off and do this proton-coupled electron transfer and multi-electron. So what we decided to do is study the downhill reaction, the fuel cell reaction, O2 plus hydrogen to water. And what I'll tell you is 5 years of hard work. What we found, and we made things like this. These are called hangman porphyrins. So we made porphyrins that could take the electron, and then we hung the proton right above the redox platform to do a long-distance electron transfer in and out with short proton hops. And what we learned, Dirac pioneered the synthesis of this, and Bob did the electrochemistry, is that if we added 3 electrons, and we had to do it in a special way. So this is cobalt-2, it goes to cobalt-3, and it gives up 1 electron to oxygen to make superoxide. If it wasn't basic enough, or this pKa was not proper, the proton wouldn't transfer. We would add another electron and make peroxide, and that kind of shunts the system. The only way we could break the OO bond is we had a couple of proton to the transfer to the superoxide. That would then drive a 2-electron reaction. I put 3 electrons in the OO bond, and that would break the OO bond. So now you just do the microscopic reverse. If I need 3 electrons to break the OO bond, it's the 3rd hole that I have to concentrate on to make the OO bond, and I have to proton couple it. So we also use cobalt, something Harry would tell you. You don't want the oxo wall, right? So if you get too early in the periodic table, oxygen does a lot of back bonding to the metal. It makes a very strong bond. So you choose a metal over there on the periodic table because those metals have lots of electrons. They have weaker metal-oxygen bonds. So from all that work, we had a rule set. Use cobalt. Of the 4 holes needed, concentrate on the 3rd hole, proton couple it, and then when you proton couple it, don't make a catalyst that's stable. And maybe a lot of you don't know this, but the photosystem II oxygen evolving complex, which is the machine that makes oxygen, the cofactor in the leaf, that cofactor is being broken down because oxygen is toxic to the plant. It starts to eat away the D1 protein. The D1 protein is a transmembrane protein that holds the oxygen evolving complex in place. The oxygen starts to eat away at the amino acids, the ligands, the arms that hold the catalyst together. So every 30 minutes, the plant removes the D1 protein, takes sulfate, SO4 2- from the ground, makes cysteine, rebuilds the entire D1 protein, sticks it back in, and then this thing self-assembles. So even the plant, when you look at those little green things out there, admire them. Because first, they're running a much harder reaction than you. You're using the energy, and they're fixing themselves every 30 minutes, and we're just decaying, right? So plants, they rule compared to humans. So we set out to do this. That led Matt Cannon, people always ask, why did we make this concoction? That led us to use cobalt, use phosphate, put it in solution, and we did a self-assembly process. Here's cobalt. It's just sitting in a glass of water. You come through here and you take cobalt 2+ to 3+. When it goes to cobalt 3+, in the presence of phosphate, you get this film forming on an electrode. The electrode could be electricity out of the wall or from a solar panel. And that film, as it forms, if you go further, you find this big oxidation current right here. And that current is water splitting, and you find out it's all oxygen. So here's the oxygen just flowing off the electrode. You can run it at 100 milliamps per centimeter squared. Sun's coming in at 30 milliamps, so you're plenty fast enough to keep up with the solar flux. And you find out it's 100% oxygen. Since our discovery, there's lots of different ways to do this self-assembly process. So we did electrode deposition, and it's always dangerous when you start adding names, because when I walked in the room, I saw Shannon Stahl from Wisconsin, and I realized his name isn't here. So there's lots of names that aren't here. I'm sorry about that, Shannon. I told Shannon I'd give him a shout out. You can do gas deposition, pulse laser deposition, cobalt onto silicon, and something that's become very popular, and this is only some of the names, you can just shine light on a semiconductor. You make the positive charge at the surface. If there's cobalt out there, it takes cobalt 2 to 3, and you actually, this is K.S. Choi's work at Wisconsin. You can see the catalyst forming on the zinc oxide. So there's lots of ways to do this self-assembly. How well does this catalyst work? And I just want to go through this quick little diagram because it's not something that chemists are familiar with unless you're an electrochemist. If you're using an electrode, that's your reactant. That's part of your reactants. So the holes or the positive charge coming out of the electrode is a reactant. If I turn the potential up, I'm going to destabilize my reactant. And this is activated complex theory, so the bigger the barrier, the slower the reaction. If I turn up the potential, I'm going to destabilize this well, and when I destabilize it, the barrier is tinier, and the reaction goes faster. So you can't talk about overpotential. How far am I beyond water splitting, 1.25 volts? You want to be near the thermodynamic potential. You also need to know how fast the reaction is going. So that's what a Tafel plot is. A Tafel plot looks at overpotential versus log of the current. How fast does the reaction go? This is a decade plot, so I increase activity by a factor of 10 as I turn up potential. And what you find about this cobalt catalyst, for a given platinum, kind of the gold standard of water splitting, at any overpotential, this cobalt catalyst, when you normalize for the surface area of the catalyst, this cobalt catalyst is 3 orders of magnitude better at doing water splitting than platinum for one simple reason. It can handle the proton-coupled ET. I'll show you that in a minute. But you can use electrochemistry to start doing kinetic rate laws. You're stuck using electrochemistry in this field because you're running a reaction uphill. So you have to put energy into the system. You can do it with an electrode in an equilibrium sense, turning the potential up, or you do it non-equilibrium, you bring a photon in. But that's the difference than what we usually do. When you're in energy science, all your reactions from the ground state are uphill, so you have to use different methods to do chemistry. What does this thing look like? You can actually have the catalyst as it's working. Yogi, Matt, Quabana, they built an electrochemical cell, and we did this at Berkeley with Junko Jano and Vital Ramachandra. And so what we did there is we put the catalyst, we made a mylar, we took a balloon, mylar, we sputtered ITO on it, we put the catalyst, we built an electrochemical cell, and we put it at the end of the synchrotron, 2-mile synchrotron at Stanford. And then as the catalyst was working, we could do X-ray absorption. And what you find is that that layer of material that looks like it's a solid state material, it really isn't. It's a molecular material. It's an oxidic cobalt cluster. And you have, on average, it's a self-assembly process, so it's not a pure compound in size, but the maximum is 7 cobalt atoms from X-ray absorption analysis. That you have 7 cobalts, and you can see the cobalt sits in an octahedral crystal field. So it's the classic octahedron of cobalt. That thing might not look like this to you. If you're not an inorganic chemist, they look different, but they aren't. They're the same. If I take manganese, replace it with cobalt, so this is the ChemDraw picture of the oxygen evolving complex, which we now know what that looks like, right? Last year, the 1.9 angstrom crystal structure of the photosynthetic membrane was solved. Not only can you see this, you can see 2,200 water molecules in the membrane. But that's what the machine is that does water oxidation, the oxygen evolving complex. If I take that, replace manganese with cobalt, and do a head-to-tail dimerization, you get that. Then rotate it by 45 degrees, and you get this. All right? In this cube, you have sodiums or potassiums that sit above this triangle of oxygens, and it's highly exchangeable. In the OEC, this is a calcium ion. So structurally, it's very akin to the photosynthetic membrane. What is it in terms of catalysis? You can talk to Dave Britt at UC Davis, actually, one of Jim's colleagues in chemistry. And Dave is an expert at EPR spectroscopy. And so we can actually run the catalyst and then go and take the EPR. And what you find is when you're at potentials below water splitting, so that's 1.03 volts, it's all cobalt-2. When you start to see lots of bubbles, you're at a potential beyond water splitting, 1.34 volts. You then look and do the EPR and you find out it's cobalt-4. And so the catalytic cycle is running between cobalt-2, 3, 4. Now you're going to get back to inorganic chemistry again. Cobalt sitting in an octahedral crystal field. And so we'll teach our freshmen, if they take freshman chemistry, that when cobalt is in an octahedral crystal field, oxygens, and it's D5, that's cobalt-4, it's low spin, the electrons are in T2G, so I'm sorry for all the non-inorganic chemists, these darn d orbitals just showed up. Can't avoid them. So there is D5, then you go to D6, cobalt-3, low spin, but we teach our freshmen when you go to D7, high spin, you put electrons in the EG orbital, and that's metal ligand antibonding. So by definition, this catalyst has to be unstable. It is. You watch the catalyst when it's operating, it's stable. But as soon as I take the potential off, I make oxygen, the system relaxes the cobalt-2, and cobalt starts showing up in solution. You can make the catalyst out of radioactive cobalt, cobalt-57, and you can just look for reactivity in solution. And then we can turn on the potential, and then it re-self-assembles. Those clusters take the cobalt from solution, re-self-assemble, keeps churning away. You can actually turn the thing off, leave for 2 weeks, all dissolves in water, turn the potential on. Within an hour, it all goes back on the electrode and just starts working again. So it's ultimate self-healing machine. You can run this out of any water source. So regular oxide catalysts decompose immediately if you use the Charles River. You too will decompose if you swim in the Charles River, so don't do it. But as soon as this catalyst, because it's self-healing, you don't form biofilms and you don't get this corrosion problem. It's always self-healing. So you can use any water source. You can take a puddle off the ground if you want, and you're good to go as long as you have sunlight. Why is it stable here when it's operating? You can do Marcus theory, and we made these cobalt cubanes. Actually, it's something George had made at University of Illinois, Florida, actually, a long time ago. And so what you have right here is the cobalt cube. Remember, we're at cobalt 4. When I'm at 1.34 volts, I'm at cobalt 4. There's a bunch of cobalt that's cobalt 3, and so the way the charge moves through the film, because it's a molecule, it's not a solid state material, there's not a band structure, the holes do hole hopping. You self-exchange. So the cobalt 4, because it took a hole from here, now propagates through the film by taking an electron from its neighboring cobalt cluster. And we can actually calculate the rate constant, and it's 3 times 10 to the 5th reciprocal molar per second. So when the catalyst is operating, the charge is sweeping out through the film fast enough relative to dissolution. So that's why it's stable. And only when you go to open circuit potential does it dissolve. Yogi and Quabbana can then set up a rate law. And so what we'll do is use this Tafel plot again. We'll look at overpotential, and then we'll look at how fast or how much current we get. And again, as you turn up the potential, as I turn up the potential, this is the potential pass water splitting, so add 1.2 volts to this. You find out the reaction goes quicker. You take the slope at 64 millivolts Nernstian. You can then do a pH dependence, and you find out it's 1 over H plus, and so I can now look at surface coverage, and I can build this rate law. And what this is saying, it's a 1 electron, 1 proton coupled electron transfer at the cobalt 3,4 state. Remember Dirac told us to break the OO bond, you should be at the 3rd electron. Yogi and Quabbana found at the 3rd hole, you do a proton coupled ET, and that's the pre-equilibrium before the rate determining step of OO bond formation. You can go further, and we can actually watch the nucleation process and growth of the catalyst, do the same type of chemistry, and then watch film growth, and you find out that that's operating with a pH dependence of 1 over H cubed. This is 1 over H. When you're very acidic, you're beyond pH 4, then the film can't form because there's a high proton concentration, so I can't actually do nucleation. When I get above pH 5, then the catalyst dominates in the water oxidation process, and the film is stable. So we know everything now about the nucleation, film growth, self-healing mechanism. This is kind of a neat experiment, pioneered actually by Tito Abrunha at Cornell. What we do is we can actually bring our solution up to the electrode. We then do all the chemistry I just told you. The solution hits the electrode, it comes out over here, and then we can flow it out here. But any gases in solution can go through a membrane, and then we can measure by mass spec what we're making. So if we make the catalyst out of O18, all the oxygens in the catalyst are O18, I put it in O16 water. If the oxygen's coming from waters that dock to the catalyst, I should get 32O2, 216 O's. If it's both oxygens coming from the catalyst, it should be 34O2 or 36O2, 18 plus 18. We see 34O2 as we scan the potential. So literally, as we scan the potential and we get into water oxidation, we're not detecting current now, we're detecting the mass spec of oxygen. That tells us here's the proton-coupled electron transfer step at the 3rd hole where Dirac told us to look, and Bob. We then get the rate determining step, and that oxygen came from a water in solution. It docks at the cluster. The other oxygen comes from a bridging position oxygen. That leads to 34O2. We come back to cobalt-2. If the film isn't too thick, 100 nanometers is fine. You can sweep the charge through. It's stable. If you turn the potential off, a little cobalt comes out of solution, but you can re-self-assemble. So this is a weird catalyst. You guys are taught catalysts aren't used up or made in a reaction. You can't call that a catalyst. The catalyst is the thing plus 200 millivolt overpotential, so I can do self-healing, right? So it's the thing plus an energy input. So when you do self-healing catalysts, you're going to have to rewrite your textbooks. That's making O2. How about hydrogen? I need to now make hydrogen. In that original movie I showed you with Matt, we were using platinum. Well, this is pretty easy to solve this problem. I'm in a glass of water, so you can make a catalyst out of nickel, molybdenum, zinc. They all have purposes. Nickel makes hydrogen, does the heavy lifting for H2. The problem, if you put nickel into solution with phosphate or borate, the phosphate and borate lay down on the catalyst and they passivate it. So what we do is we put a soft metal in there, zinc, hard, soft, acid-base theory, Basolo and Pearson from the 60s. That's a polarizable metal. You have a hard anion, hard, soft. They don't like each other, so we shift the equilibrium of the phosphate and borate off the solid solution. That leaves nickel there to do heavy lifting. What's the molybdenum doing? The molybdenum's in there, and over a few days we anodize it out and we make this highly porous material. That's called dealloying. So that gives us a high surface area. This stuff works great at 35 millivolt overpotential. 35 millivolts past the hydrogen couple. We can run it 1,000 milliamps per centimeter squared. So this is the electrolyzer you can buy off Google. From that discovery in 2008, last year we made an all-plastic electrolyzer. It's not the fastest, it's not the best, but it can keep up with the sun, and it's really cheap because we're just using simple materials in water, simple membranes. So it's very easy to start driving costs down, all because you've made some new compounds that have self-healing. Can you keep going? Because in this electrolyzer, you got to hook it up to a solar panel. Solar panels cost money, but again, you guys now know that manufactured goods go by weight. The silicon is only a tiny piece of the weight of a solar panel. It's everything else. This will be coming out in the MIT solar study. It's all the other balance of systems costs that drive the solar panel up. So can I go in there now and take the heart of the solar panel out, silicon, and build now a hamburger? All right, so here's going to be the hamburger. That's the patty. I'm going to put a piece of cheese, the transparent conducting oxide, because if I'm making O2, O2 plus silicon is going to make SiO2. That's got to pass the charge through, and then I'm going to put the catalyst, the top bun and bottom bun, the cobalt catalyst and the nickel on the bottom. And so that's what Yoop did. He was a physicist from Holland. He came into the group and took boron-doped silicon, P-doped silicon, and then we doped it, P-doped it. This is no new science. This is standard electrical engineering. When the sun comes into the silicon, the electron has to go one way and the hole has to go the other. So you have to put a heterojunction. The heterojunction puts an internal electric field, so you can ramp electrons one way and protons the other. You put a P plus aluminum layer, it helps the holes go faster or transport and get out of the silicon. It's still a single heterojunction, NPP plus. A single junction of silicon puts out 0.7 volts. You got to 0.6 volts. So that means he has a pretty good piece of silicon. So if I shine sunlight on it, I get 0.6 volts. And it runs at 27 milliamps per centimeter squared. I told you on the sunniest days, you're 300 watts per meter squared. 300 watts per meter squared will come out to 30 milliamps per centimeter squared. So this silicon can keep up with the sun, but it can only put out 0.6 volts. So we need to put electrodes on it because I got to get to 1.3 volts to do water splitting. So I'm going to have to put potential into this. We coat the silicon with ITO. We now use FTO because that's cheaper. We put it in solution. We do the Matt Cannon experiment. We put this in solution. Cobalt-2 goes to cobalt-3. The catalyst forms on a transparent conducting oxide. And now this thing makes oxygen, just like you saw before. This is the silicon now acting as an electrode, no sunlight. And we're getting exactly the same current characteristics we did before. The big difference is if I turn sunlight on now, the silicon is going to generate 0.6 volts. So for a given overpotential in the dark, when I turn the sun on, I can generate a potential inside the silicon. So now I'm capturing solar light in the potential of silicon. And it turns out at every potential, we get 0.52 volts of UPS 0.57. So we're getting almost all the potential out of the silicon. So I don't have to drive it as hard, and I'm storing sunlight. What happens if you wires two cells together? So here's one cell, I wire a second cell. Now I should get 0.52 plus 0.52, it's 1.04. I need 1.3 to split water. That means I'm 0.3 volts away. Things look perfect, right? Now I only need to put in 0.3 volts of current from the wall when sun is shining on it. This isn't rocket science. If I add a third cell, I shouldn't need any more wires, right? I can put this in a glass of water. My silicon is operating in simple conditions. So the question is, can you do that? We get a solar cell from Zunlight. Zunlight has engineered this triple junction silicon. So amorphous silicon has a strained silicon lattice, so that absorbs over here. If you put germanium in it, you relax the strain, that moves the absorption spectrum over to here. You put more germanium, it's here. So these guys did a heck of a job at engineering the solar spectrum. So you're doing the semiconductor free of catalysis. Now I put my catalyst on there. This, remember, single junction silicon puts out 0.6 volts. I have triple junction. I should be at around 1.8. I had 30 milliamps per centimeter squared. Divide by 3. I should be at 10 milliamps. It's 8. So everything looks perfect here. This solar cell is a 7% solar cell. I now bring sunlight into it. I've made my hamburger, so this really looks like a hamburger to us. It's just layers. And I can drop it in a glass of water. I do this because I just like looking at myself during my talk, I'm sorry. So I actually made a movie at Sundance, and the guys that were doing the movie, the producer said, "No, sir, show me that this works. Just drop it in the water and go up to the window." So I did. And so what this is, oops, I can't hit this button. Wait a minute. We're almost done. So that now is just the piece of silicon coated. We've dropped it in a glass of water. Sunlight's coming through. The holes are coming to the front surface. That's where the cobalt is. The back side has the nickel catalyst. The electrons are going there. So just like the leaf, sunlight in, wireless current. You do it 4 times. You store 4 positive charges in the cobalt, 4 negative charges in the nickel molybdenum zinc alloy. You split water. You make O2. The protons run around the backside where the electrons are waiting for them. Hydrogen comes out. You've spatially separated oxygen over here, hydrogen here, so you don't have any collection problems. And it works using the sun. And it's running at 30 milliamps per centimeter squared. The overall efficiency, so you can find movies like this. They've been around forever. People show them all the time, but they're scamming you because they're using a wide bandgap semiconductor. So this is what's called the IV curve of the semiconductor, the current voltage curve. Because it's a wide bandgap, say 3 volts, I showed you some of those at the beginning of the talk, Here's the IV characteristic of the catalyst. We now know that's called a Tafel slope. So if I look at the IV characteristic here, it's where the two intersect that I should get my maximum power efficiency for sunlight to fuel. If you have a 3-volt semiconductor, most oxides, you have all day to get to the top of that curve. You can have the junkiest catalyst in the world, you never notice it. And you do use the junkiest catalyst in the world. You use the oxide. And I told you those things can't do the 4-proton, 4-electron transfer. This red curve is the power curve for the Zunlight solar cell. There's my Tafel slope. It intersects at 5%. For a 7% cell, sunlight in, I'm doing a 70% conversion of chemistry to solar fuels being driven by the solar cell. It says 5. When you measure the amount of hydrogen and oxygen, you're 4.9%. How do you, and you don't want to make this curve go away from the thermodynamic potential, because the further out it goes, the less sunlight it's absorbing. So you're always stuck in around this gray bar where water oxidation occurs in these buried junctions. So you have to be really good at catalyst design and proton-coupled ET to get this curve to rise sharply, meaning you got to do that 4-electron, 4-proton chemistry. If you look in JAX in the last few weeks, you're going to find this new catalyst we did, a nickel borate. I told you this cobalt was Nernstian, 1 electron. So remember Nernst's law, N is in the denominator. If I make a catalyst where the resting state is a 2-electron, 2-proton, N's in the denominator, I should go from 60 millivolts to 30, a steeper curve, and lo and behold, it works, and you get even a more efficient cell. Now, depending on what solar cell we're using, we're running at 85 to 90% efficiency, sunlight into solar fuels. If you want to go to 10%, what should you do? Don't use a 7% cell. Now you should go and use a 12% cell, and then you'll be at a 10% efficiency. So we're doing that right now. Next to last slide, the one other thing we're doing, we now have a really simple way to make catalysts on silicon in a buried junction device, drop in a water at work. What's the next goal? Can I make this under high throughput manufacturing conditions? At Harvard, Professor Roy Gordon, my colleague at Harvard, Roy is one of the pioneers of chemical vapor deposition. He has the patents on e-glass, you know, the energy efficient glass using CVD. People like Corning, glass companies can run CVD, automobile companies, all your glass in your car is treated by CVD, runs at 1,000 meters per minute. Look at what Corning just did. They've made this stuff called Willow glass. It's totally flexible glass. So one thing you can look for in the next year or two is Roy and I working really hard. Roy's also interested in getting rid of the amorphous silicon. Amorphous silicon, there are no big plants making amorphous silicon. They make crystalline silicon. So in my labs, we're building crystal silicon cells. But Roy would like to get rid of the silicon and just spray a semiconductor with the right band gap down on the glass as it's going by. And then we're working with him and his group to make the cobalt and the phosphate precursors to just build everything just by spraying as the glass is going by. And that will increase the manufacturing rates and make this cost even drop further. So those are sorts of some of the things you can look for. So I'll end with belief. We really like it, if nothing more, to show that if you start with a blank piece of paper, we looked at where cost was, and that told us what science we needed to invent, self-healing catalysts, layers, buried junctions, control the interfacial charge transport. I'm not showing you all of that to make this thing work. And then you get something, there's no wiring, no membranes. By the way, if the protons have to run around the back, that's an ohmic problem. So what you do, just poke holes through the silicon. They don't have to run around. You know, this gets pretty simple now. Works in any water, simple engineering, highly manufacturable. It really looks like a hamburger to us. So Unfortunately for Harry, I think he had greater plans for me, and my life ambition was to be the McDonald's of energy systems. I wish I could have done prouder for him. But we just wanted to make the hamburger of energy. And I'm going to end with this final quote, and it's Mr. Tata. So Mr. Tata's company, Tata conglomerate, has built most of India. And his grandfather and his family started this company to take Indians from poverty in the 30s and elevate them to an emerging and rising middle class. That's what that company exists for. And then they happen to make money. But when Mr. Tata gets up in the morning, what he cares about is how do I employ Indians and make my country better. That's a $140 billion conglomerate now. Okay? So you can make money, but that's not what drives him. And he's been imploring all of you to start doing science that appeals to the poor, meaning you got to get up in the morning and think a little differently about what science you're going to do for them. Just to give you a little heads up, in India alone, in the next 25 years, there'll be 352 million people coming from poverty to the rising middle class, which is the entire population of the United States of America. So to get back to the idea of Brian Furness, you better take care of them if you want a sustainable planet. And the way to do that is to give them food, water, and energy at low cost. And that means invent, invent, invent. So with that, thank you for your attention.